we have a problem. We have too much time just to finish the last subject we did, and too little time really to start a new subject toward the end of the semester. So what I'll do very quickly, I will end up with what we did last time. And then, last time means not the lecture of Rome, but 2 weeks ago. If you remember, we were in the middle of proving that the Ramanujan graphs, on one end, we showed that they have large girth, and I did half of the proof, and I will not bother to do the second half. Though the second half is some, you remember what I'm talking about, or you all forgot? We define some graphs, x, p, q, which were the Cayley graph of PGL to Q. Well, not exactly PGL. We define a subset. I don't know, maybe I should skip it if you don't remember, because now to get you it will take too much time. Okay, I'll just say what was the story there. We defined a set S of size P plus 1. S was a subset of PGL to Q, and H is the group generated by S, and there are two possibilities. Either it is PSL to Q, and this happens if P over Q is 1, namely if P is quadratic residue mod Q, and it is PGL to Q when P over Q is minus 1. Okay? And what we claim, we really was that if we look at the Cayley graph of H with respect to this S, then the girth, so if this is XPQ, then the theorem was that the girth of XPQ is greater or equal 2/3 log to the basis P of N. N is the size of H, the size of the group, so the number of vertices, if PQ equal 1. And this we proved. And the second part is that the girth of XPQ is greater or equal 4/3 log P of N if P over Q is minus 1. And this we didn't finish. The plan was to finish it when that. But I tell you, I don't think, I mean, in some sense, this is the most, that's a quite remarkable result. I mean, it's improved only by a constant, but I think I told you that this is a very surprising result, because this result is better than random. This, you see, the degree of the graph is P plus 1. So log is log to the basis K minus 1. And recall that the girth must be of XPQ is at most 2 log P of N. And that's a very simple, I think, Moore inequality is called, but it's a trivial exercise, I showed you that. And it's a big open problem. Can you really improve this to a smaller one? And as I said, this was a result of Erdos, that you can get graph with large girth. Large girth, by random methods, people achieve one time log P of N, kind of half the way to the optimal. And these results beated the random, which is a kind of a rare property in combinatorics. Usually in combinatorics, you try to do as good as random. That's what you hope. And this would be the, but the proof of that is basically the same proof with this little trick using the fact that it must be even or something like that. I don't want to remember, it will take me too much time. I mean, you can read in my book, for example, or in the original paper of Sanak, Phillips, and mine. But there was another property which I promised you, and maybe this I should do, because that's really related to expander some, and that's about the chromatic number. So the other theorem was that the chromatic number of xpq, and now, of course, the chromatic number of xpq is equal to if pq is equal minus 1. Why? Because this is a bipartite graph, if you remember. That's what we said. That if it's PGL2, it's bipartite graph. We have a subgroup of index 2, which is PSL2. All the generators are outside, and they are flip-flop from one side to another. They take you, one side is PSL2, the other side is the coset of PSL2, and all the generators take you from one side to another. So that's not interesting. The really interesting is that chi of xpq is greater or equal to something like p plus 1 over p plus 1 over 2 square root p. So now, when p goes to infinity, we get graphs with q goes to infinity and q goes to infinity with arbitrarily large GERT and arbitrarily large chromatic number. And this is also a quite remarkable property, because if you think about it, it's quite counterintuitive. You see, if you have large GERT, then it means that locally you look like a tree. If locally you look like a tree, then you can color the graph only by two colors. You start with black, white, black, white, black, white, and it walks all the way quite far. And suddenly you cannot do it anymore, and it collapses. And if you check, I don't want to get to this. If you check it, you can really do it like quite one can estimate what the diameter of these graphs, and you can do it really far. When I say far, up to some constant time the diameter. If you look at the GERT is constant time the diameter, which means that like I can go half of the diameter, say, and it's look like a tree. And only after that, and from every point this is still true, and only after that there is some problem started, and they started in such a dramatic way that the chromatic number it's getting very large. And again, this was a famous problem. Even Arder, many years ago, Arder graph with arbitrarily large GERT and arbitrarily large chromatic number. It was solved by Erdos using random method, and I believe that at some point Lubotzky gave a constructive proof, but not an explicit proof, in the sense that he showed an algorithm that will give you such graphs, but it's not explicit in the sense you can describe it. And here you get very explicit example, and I think also the parameters are better than what was done before. Unlike the GERT, and that's what I want to show you for a few minutes, unlike the GERT issue, which was very elementary, we didn't use any deep stuff. Here we have to use this Ramanujan bound that I told you about. I told you that these graphs are Ramanujan.
Alex, do you know what is the chromatic result for the Bouguin-Gambord construction?
Okay,
because it looks like this follows from pseudo-randomness, not from
right, but
the less step.
Right. I mean, it won't be as good as this one,
obviously,
because the Gambord-Bouguin. First of all, you have to, in order to get the chromatic number large, you have to deal with the number of generators going also to infinity.
Okay.
Now, but
This
that's
is not
fine.
a problem.
But that you can do it also. But what they get, they only get that these are expanders.
But they get large gaps. This is part of
They
this
get large
is
gap, but they don't get, you see.
And they get a spectral gap, a very small.
No, but the spectral gap, you see, the spectral gap should be a little O of P. That's I'm not sure that they're getting.
They get explicit spectral gap. but
No, they
very
get explicit for,
non-good.
no. They get, they usually do it with 2, because to prove expander it's enough, right? If you take P, you get 2. But here you need, you see, I'll show you what you need. You need the ratio between the second and the first and the second goes to infinity. And this is, I don't think, I'm not
in
sure.
subgroups it's not true, you're saying?
What?
You're saying that in subgroups it's not true? That is still...
I'm not saying it's not true. I'm saying I think it's not known. I mean,
There is some results about the spectrum by Lux Phillips, all those...
I don't think they have this.
Maybe you'll show us the proof.
I don't think they. Yeah, okay, I'll show you the proof. The proof is really using the Ramanujan, not just the expound. I mean, you don't need the full Ramanujan if it's what be square root of something.
Yeah.
But you want this to go to infinity, which means that you need that this second eigenvalue will be.
It's not second. There must be spectral bound from both sides.
Yeah, but I think both sides they probably can
They're
get.
not bipartite. It's not.
Yeah, probably, both sides they probably can get. That's I'm not worried about. What I think they cannot get, I don't think they can
The
get,
second
but it will be the ratio. I mean, maybe I'm wrong, but I don't think so. Okay, so let me prove this quickly. I mean, I plan to spend on this like 15 minutes, and I'm now start to worry that it will take okay, so. We can prove it in 2 ways. Proof 1 is just to quote the results of Hoffman. Hoffman inequality, but in fact I basically will prove you this Hoffman inequality, but I'll just say that you know that in general, if X is K regular graph, so you remember that the eigenvalues are between K and minus K, then the chromatic number of X is at least K divided by minus lambda n minus 1 of X plus 1, where the eigenvalues are lambda 0, this is K, lambda 1, up to lambda n minus 1. Note that if lambda n minus 1, that if X is bipartite, lambda n minus 1 equal minus K, and we get chi X greater or equal to, and indeed it is 2. Because if you are a bipartite graph, then the chromatic number of a bipartite graph is 2. You can color one side with black and one side with white. But now, in our case, X PQ, the PQ equal 1 is not bipartite, and lambda n minus 1, we know this is inside the minus 2 square root p to 2 square root p. That's exactly the Ramanujaness. Right?
How do you know it's negative?
Oh yeah. It's impossible that all eigenvalues will be positive.
Some of the eigenvalues is the trace.
What?
The sum of the eigenvalue is the trace and the I don't know. We're talking about the
It's adjacency.
The adjacency matrix, so the trace is zero.
That what?
The trace is zero, so the subset.
Why the trace is zero?
Because it's adjacency.
The
It's not
adjacency
zero.
Right. Right, the adjacency matrix, there are no loops, so there are no, everything is zero, so the trace is zero, so the sum element is zero, and therefore there are negative eigenvalues. Yeah, sorry. Yeah, good thing. I forgot. I remember it's easy, I forgot one. Okay, so chi of x pq greater or equal p plus 1, which is k, divided minus lambda n minus 1 plus 1. So we can replace it by something which is bigger. So this is greater or equal than p plus 1 divided by 2 square root p plus 1, if you want it. Okay, but basically now I will prove you this Hoffman inequality, or maybe I think because I want you to see that this is really related to expander, that how the eigenvalues are really playing a role here. So it's not really proof 2 in some sense, is elaborating on the proof, but let's define I of x, the independent number, of a graph is equal to the maximum subset size, the maximum of the size of a set A, so that A is a subset of V, such that no two vertices in A are adjacent to each other. What's the maximum size of a subset of the graph such that they don't touch each other? They're not neighbors of each other. And clearly, let's think for a second, the chi of x, the chromatic number, is at least n. N is always the size of V. So V over I of chi, since every monochromatic subset is independent. Right? If I do have some coloring, of the chromatic number of the graph with the right number of colors, which is the chromatic number, then every subset is independent, and therefore the number of independent sets, so the size of it is at most this one, and therefore the number chromatic is at least V over this. And now let's prove claim or proposition, which is kind of important by itself, that if X is Ramanujan, a K regular Ramanujan, say K regular Ramanujan, not bipartite, and we'll see how this will come up in the proof, not bipartite, then I of x is at least 2 square root, is at least or at most? I have most. Well, there is a mistake in my name. Is at most 2 square root k minus 1 over k times n. Right? We have basically It should be at most, because if it's a graph, it's expander. It's a very intuitively we understand that there should be some connection like that, right? Because if the graph is expander, it means that it behaves like random. If I take a subset which is very, very large, then there is a good chance that two elements will meet each other just like in a random graph. And now if we put the proposition, so from the proposition plus this observation, we get that the chromatic number is at least V, which is n, divided by this, and then it will be at least k over 2 square root of k minus 1, and that's exactly what I wrote. Right, so this implies the same proposition. Proof, but it gives us a little bit more, because now we know also an upper bound, an explicit upper bound on independent set. As I say, let be an independent. Now we will apply the same trick we applied about expander. An independent set of size R. Define a function f. Let f of x be equal 1 on A and minus c on A bar on the complement, such that c will be so that r plus n minus rc is equal 0, namely c is equal minus r divided by n minus r, and we choose c like that, so this means that f is in L to 0 of x, right? F is a function which sum up to 0. This is a function which sum up to 0. So we know we get it sum up to 0, and now we know. So now we know that when we apply the adjacency matrix or the Laplacian, if you want, if now A, how did I call the adjacency matrix? A or delta? So maybe I call this B, don't mind, because A, I think, was the adjacency matrix. So if A equal the adjacency matrix of X, this is the n by n matrix, which then what we know? We know that A of F norm by L2 norm square is at most 2 square root of k minus 1 square norm of F. Why? Here I'm using that the graph is not bipartite. Let's be careful, okay? Since F is in L to 0, those which, remember the function which sum up to 0, these are exactly the functions which are orthogonal to the constant function. The functions which are orthogonal to the constant function are exactly the functions that A acts, I have an orthonormal basis with respect to the eigenvalues. All the eigenvalues are k, no minus k. There's no minus k. That's very important here. I'm using it now. There's no minus k. Eigenvalues are either k or all of them are in absolute value less than 2 square root of k minus 1. And on the space of function orthogonal to the constant, namely the functions are that L to 0, which sum up to 0, this is exactly the function orthogonal to the constant. The matrix acts using this eigenvalue. The largest one is 2 square root of k minus 1, or maybe even smaller. but it's less than that. So the action on the L2 norm is at most this one. And now we're just spelling out the meaning of that. So let's see what does it mean. On the other end, as B is independent, then let's think about it. We see that A of F on X is equal minus CK if X is in B. What happened? What is A of F on a vertex X? You sum up on the neighbors. The neighbors of B are all of them outside B, right? Because B is never a neighbor of itself. Then all of them are getting minus C. So, so this means, and therefore, if I only sum up on these, it means that AF square is at least C square K square R square. It's even more because I sum up.
What's R, the size of B?
What?
R is the size.
Yeah, because I sum up.
So no square.
I sum up only on.
No square only.
No square. I sum up over.
Larger.
Larger. Right. I sum up over the. I sum up on the norm of AF only on B. Right? Okay. If you want to sum up over X in B of AF of X squared. And this is equal to this. Okay. Now we know that C is equal minus R C equal minus R over N minus R. Let's write it, I write it as V over 1 minus V, where V is the proportion R over N. We'll see in a minute, this will be convenient. These are the little tricks. And let's write it. So C square K square times R, which is the norm of AF. It's right. It's less or equal AF norm, and therefore this is less or equal 2 square root K minus 1 square, the norm of F. But the norm of F is very easy to compute. This is equal, first of all, let's open this, 4K minus 1. Now, what is the norm of F squared? F is a function which are getting only two values. It gets value 1 on B and minus C on B. So, so the norm of it is R times 1 square plus N minus R times C square. Okay, and therefore we get it C square K square R. You see, I
think that's a lot.
yeah, N minus R, N, V equal N, N, I can cancel R, but I want to say N minus R divided by R, this is minus C. I'll tell you what is written here, and then we'll try to justify it. K squared, what I have here is that this is 4k minus 1 times 1 plus c squared 1 over v minus 1. Okay, let's see. So it seemed like we divided by r. We divided by r here. We divided by r here. We have to divide this by r. If we divide n minus r divided by r, we are getting
1 over v. Okay, this is
1 over v minus 1 should be equal to n minus r over r. This is true?
Yes.
Okay. This is true, and this is true. And therefore, now, now this is, the continuation is just kind of a little game, that v squared divided by y minus v squared, k squared is at most 4k minus 1 times 1 minus v squared. I don't know, probably there is a better way to do it. I don't know why it looks to me like nothing way. And then we get, I'm just copying from my notebook, but to be honest, I don't remember. But I think I checked it. I copied, of course, from a paper, but I think I checked it when I wrote it. And therefore, we're getting v squared. K squared is at most 4k minus 1. And now we are getting to the important, that v squared is at most 4k minus 1 divided by k squared. And nu is at most 2k minus 1 divided by k. And that's a crucial, you see, nu is the relative size of the independent set with respect to the full set. Okay, I don't want to waste time going over that. It's probably
So here you cannot, by this method, you cannot do better because these are Ramanujan graphs. They have the.
This is the best method that you can.
This is the best you can hope for any graph using this.
Using this method, using the spectral method. But I don't know. No, I'm not sure if you cannot do better by for Ramanujan graph using other things. We don't know what the, and, well, I think. No, I don't think it's known. The GERD is known that for the Ramanujan graph, I think the 4/3 is indeed.
And here the chromatic number you bound using the independence number.
Yeah.
And the is the.
But Hoffman, which original proof of Hoffman was by a different method. But was a different method.
But it's all.
But it gives you exactly the same result.
But for independence number, so if there is a gap between the chromatic number and the n divided by independent method number, then you cannot. And the other, I mean, do you know what? Can you color the Ramanujan graph with?
No.
With this number?
Explicitly?
Yeah,
I have no idea, of course not.
Or find independent sets and then.
Very good problem, but I don't think so. I mean, here is even somewhat, it sounds easier. We know that the diameter is small. Can we find an explicit
Yes.
band?
What about this?
A lot of, many people made efforts here, let me mention to you, but I want to talk, take the group SL2P, and it's known that this group is expanded with respect to the two generals, 1, 1, 0, 1, or 1, 2, or 1, 1, say, and 1, 0, 1, 1, which means that every matrix here can be written as a word of length log P, using these two generators, but nobody knows how to do it. I mean, even for this, take the following matrix, 1, P minus 1 over 2, 0, 1. This is clearly equal to 1, 1, 0, 1 to the P minus 1 over 2. So it's very easy to write it as as a word using the two generators. In fact, one is enough. But this is a very long word. Easy to write it, but it's a long word. But we know that you can do it in constant time, and explicit constant, 500 will be enough. Log p, but we have no idea how to do it. A problem for first year undergraduate, right? Okay, but I'll stop here. I want to spend the rest of the time, either before the break, if you want to take a break now or that, basically to describe you, we'll come back to that, I-dimension generalization for that. But somehow to give you the, so we studied the Ramanujan graphs in quite details. We already talked, if you remember, about buildings. So now we want to do to the buildings what we did for the graph, for the tree, right? We had the Boatitz tree of SL2. We divided it by some very explicit discrete group. We got finite graph because of something which I didn't explain, but somehow the Ramanujan conjecture. We had bounds on eigenvalues of that, of this graph, and from this bound on eigenvalue, another property, we deduce various geometric properties of the graph, right? Now we want to establish such a theory for higher dimensional simplicial complexes. Namely, we'll start with a building, we'll divide it by some groups, we'll get finite simplicial complexes, and there are various problems that we want to study. And this will be done in the second semester. So in some sense, the rest of the talk today will be a preview for the second semester. If you want, we'll take a break now, or I should start and then take a break?
Let's take the break now.
No, it's maybe natural to take the break now.
Yeah.
Okay, so let's take